Kia ora and welcome to this video on question 4 of the 2018 Scholl Calc exam. 3 parts, all very algebraic, and hopefully the video is a fairly short one because the problems aren't too bad. Okay, so the first question, an inequality involving logs. The first thing we should do is think about the values of x that aren't possible. There are ways of solving equations that involve complex values and logarithms. You can also solve trig equations like sine of x equals to 5. It doesn't have a real solution, but it has a complex one. But that's beyond the scope of level 3 NCA. So this question says find the values of x. It's implied that we're looking for real values. So for them to be real values, these two arguments have to be positive. So we know that 4 minus 2x is greater than 0 and x is greater than 0. That automatically tells us that x has to be between 0 and 2. It can't be anything else. If it is, then the log expressions are not defined. Now, students who understand logs and their inverse functions know that log base 3 and 3 to the power are opposites, but a common mistake students make is to go and get 3 to the power and 3 to the power every single term individually. The easiest way to explain why that's not correct is because if we have Pythagoras Theorem, for example, a squared plus b squared equals c squared, we don't cross the squares off. It absolutely butchers the Greek. The Greek man would be rolling in his grave. That's just bad maths. But what we can do, when we have a squared plus b squared equals c squared, we can square root the whole side of an equation. And it works. But then we obviously don't go cancel, cancel. That doesn't work. So if I wanted to, I could take 3 to the power of the whole left-hand side of this equation and 3 to the power of that. But I do need to simplify the logs first. I use the product rule to do that. I turn the logs, two logs that add together is the log of a product. And then I can do the 3 to the power thing. 3 to the power is knocked off the log base 3. So we end up with 4 minus 2x, x, and then 9 on the other side. And the question is, do I need to flip the inequality around? And it turns out you don't need to, because the 3 to the power of x graph is an increasing function. So if I have two values a and b where a is less than or equal to b, the 3 to the power of a will be less than or equal to 3 to the power of b. Okay, so the order of the inequality stays the same when I take 3 to the power on both sides. I don't need to worry about it flipping like I do with negative numbers. So we end up with a quadratic equation, minus 2x squared plus 4x minus 9 less than or equal to 0. And this is a upside down parabola, and we need to find out where it's less than or equal to 0. It turns out, it's a trick question, it's always less than or equal to 0. If I find the discriminant of it, b squared minus 4ac, so 16 minus 4 times negative 2 times negative 9, I find that discriminant is negative. So 16 take away comes out to be negative 56. It's a negative discriminant, it's an upside down parabola, so we're dealing with something like that, where it is always less than or equal to 0. So it'd be really easy to then go, therefore, all values of x work. All values of x make this equation work, but except for the values of x that we ruled out earlier. And that's like a really clunky way of writing it. All values except these. So what values do work? the solution set is x belongs to the real numbers such that x is between 0 and 2. Okay, we could look at Desmos to create a graph of that. You can do this on your graphics calculator as well. If I first up find my log base 3 function, I'll tell you in a sec how to do this on your calculator. 4 minus 2x, and then log base 3 of x. Okay, that function there is always underneath 2. So the left-hand side of the equation is always satisfying the right-hand side of the equation, less than or equal to 2, but the function's only defined between 0 and 2. As you can see, there's some asymptotes, so hence why our answer is restricted to those x values. On your graphics calculator, if you want logs of other bases, because you'll know that the log button stands for log base 10, and the ln button stands for the natural log or log base e. But any other button, you can go press the option button, look for calc, and then there's a log AB button. And if I wanted log base 3 of x, then I'm going to go log AB 3 comma x, and that's how I would graph it. That button was hiding for me for years, and then some student found it. It's been useful ever since. Okay, second question. Show that the circles x squared plus y squared, blah, 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 and the other one are tangential to each other. I'm just going to straight away look at a graph of this, because it's going to help us solve the problem really nicely. We'll look at two ways of solving this though. I should have prepared this earlier. One circle. Okay, the other one, zoom out. Oh, yep, they are tangential to each other. We can find the point of intersection, 1.538, 7.308. Turns out they're fractions. Now, method 1 is going to be an algebraic one, and then we'll look at how we can do it geometrically. So, okay, if I take these equations and solve them simultaneously, there's heaps of ways of solving simultaneous equations, but for this, I think getting rid of the x squared and y squared term would be useful. So if I subtract these equations, x squareds cancel, y squareds cancel, we get negative 24x, we get negative 10y, be careful there, it's minus 20y, take away negative 10y, and 110 equals 0. We can rearrange this equation. Okay, and the question is, what does this equation here mean in the terms of the problem? And if I graph that, it's equation of a line. If you wanted to do this on your graphics calculator, you would need to make y the subject of both the circles to be able to put them into the graph part. You could use the conics area, but you can only do one circle at a time if you do. But it's the tangent. Turns out that line there is the tangent of the two circles. It doesn't prove that the circles are touching though. If we substitute this into, let's sub it into the second circle. So I replace the y's with this expression. What I'm now doing is finding out where the tangent meets the circle. That leads me to another point. I could have used calculus to solve this problem. I could have done something with finding gradients and equating them, but it isn't as nice as doing it this way. Okay, and if I expand all this stuff out, get 6.76 x squared minus 20.8 x plus 16 equals 0. I hope that's right. I'll just check it. You'll know it's right because if you solve this quadratic on your calculator, it gives you one solution, and it does. It gives me x equals 20 over 13 repeated. Okay, there's only one solution, and then we can find the y value by using any of the two equations up there, but probably the yellow equation's nicest because it's a linear equation. Minus 2.4 times 2013 plus 11. And that gives me 95 over 13. And 95 over 13 is 7.307, so it matches my picture. Okay, so that's the point of intersection. There is only one, so it must be that. Geometrically, if we complete the square on the equations of the circles, so we're going to get x minus 8 all squared to take away 64, plus y minus 10 all squared to take away 100, plus 115 equals 0, gives us this. Okay, that's a circle that's centered at 8, 10 with a radius of 7. And I can show that on the graph here. 8, 10. There it is, there's the center, and it's a radius of 7. The other one, okay, if I complete the square on the other one, x plus 4 all squared minus 16 plus y minus 5 all squared minus 25 equals, oopsies, plus 5 equals 0. Rearrange that one. That equals 36. That's a circle that's centered at minus 4, 5. With a radius of 6. Okay, there we go. Now, the last part to prove that the circles are tangential using this approach, what we could do is look at the distance between the centers. The distance between the centers, well, in the x direction goes from x equals minus 4 to x is equal to positive 8. So a distance of 12, and in the y direction it goes from y equals 5 to y equals 10, so a distance of 5, and Pythagoras tells us that 12 squared plus 5 squared square rooted is equal to 13, and that turns out to be the sum of the two radii. The radii of the first one was 7 and the second one was 6. Okay, and 7 plus 6 is 13. So because the sum of the radii equals the distance between the two centers, the circles must just be touching. And then to find this point of intersection, we use similar triangles. We start off with the coordinate at the bottom left, the center of the left circle, minus 4, 5, and we add on 6/13. How am I going to do this in a different way? No. The x value starts off at minus 4, and we have to add on 6/13 of the change in x. The y value starts off at 5, and we add 6/13 of the change in y. Okay, so if we work that out, minus 4 plus 72 over 13 gives us 20 over 13, and 5 plus 30 over 13 gives us 95 over 13, and that's the point of intersection we had earlier. So quite a neat approach if you look at it graphically first, but in an exam it's a little bit harder to do that, I guess. Okay, last question. Find all the solutions, both real and complex, for this system here. You could make a picture of this as well, but it's only going to show you the points of intersection that are real. And it turns out that this equation has complex solutions as well. So we'll just jump straight into an algebraic approach. X squared plus y squared plus 3x plus 3y equals 8, and xy plus 4x plus 4y equals 2. So check I've got that right. Cool. Now, there is a sneaky little trick in this problem, and that's the xy term. We want to get rid of it. And to do that, we complete the square on the x squared plus y squared part. So equation 1, I can write equation 1 as x plus y all squared minus 2xy. The second part of it, I've got a common factor of 3, so I can factor that out. And then I can replace the xy, because I know that xy is equal to 2 minus 4 lots of x plus y. Another thing is, because I've got x plus y's that are all over the place repeating, that's the xy term here, xy there, I'm going to change the x plus y to equal a different letter. I'm going to say let x plus y equal to u. So I've got u squared minus 2 lots of xy, but the xy is just 2 minus 4u. I've got another 3u equals 8. And this is a quadratic. U squared plus 11u minus 12 equals 0. If you get to something that factorizes, you just know you're onto a winner. U plus 12, u minus 1 equals 0. So we've got two options here. Either x plus y equals negative 12, or x plus y equals 1. Okay. I'm going to substitute these both into equation 2 because it doesn't have any squaring involved. So using the equation 2, if x plus y equals 12, then I've got x times minus 12 minus x plus 4x plus 4 lots of minus 12 minus x equals 2. And that's going to give me negative x squared minus 12x plus 4x minus 48 minus 4x minus 2 equals 0. X squared plus 12x plus 50 equals 0. I can solve it in the graphics calculator, but I need exact answers, so I'll complete the square. X is minus 6 plus or minus root 14i. And x and y are interchangeable, so if I choose x to be negative 6 plus root 14i, because they have to add to make minus 12, the y value will be negative 6 minus root 14i. If I choose it to be the other one, then the y value will be the opposite. They have to be conjugates. X and y are interchangeable because in the original equations, the coefficients and the transformations of x and y. So x and y has been squared in the first equation, but both of them are being squared. In the second part of it, they've both been times by 3. So there's the symmetry in the problem that says that x and y are interchangeable, and so they'll be the same. We'll get answers that are symmetrical. Okay, the other one is if x plus y equals 1. So if I sub that one into the equation 2, expand it out, got x squared minus x minus 2 equals 0, x minus 2, x plus 1, so x is equal to 2, or x is equal to minus 1. So if it's 2, then the y value is minus 1, and if it's negative 1, the y value is 2. So there are 4 solutions to the problem. Solution 1, solution 2, solution 3, solution 4. 2 real coordinates and 2 complex ones. Catch you in the next video.